we are going to start streaming as well. Give me a second. So we're live. I'm gonna post about these. We are live. Yep, we're live. All right. I have to figure out a way to improve my setup somehow, but it's fine. Okay, let's go. Let's let's basically go back to where we were. Let me open the speaker and see where we are now with these. Cool. Hopefully you can hear that as well soon. And we are now in the why do we reverse in the chapter 3. We worked on these yesterday.
You're moving toward erasure as an irreversible.
I will come back to these. I might come back to these.
You're connecting the minimum erasure energy to the power draw of real hardware circuits. What leads you to tie the fundamental lower bound to practical circuit operation, rather than a physical limit set by temperature alone?
Let's go back here. Sorry, Grok. Let's go back here. Need to fix the EG stuff. Anyway, why do irreversible operations like bit erasure lead to heat dissipation according to Landauer? First of all, let's check heat dissipation and Landauer, because I don't really know much about these. So let's ask Grok, do some reading before. What am I looking? Yeah. All right. Do we have
Landauer's principle, proposed by Rolf Landauer in 1961, gives the fundamental lower bound on heat dissipation in computation. It states that any logically irreversible operation, most importantly, the erasure or reset of one bit of information, must dissipate at least a minimum amount of heat into the environment. The Landauer bound formula. The minimum heat dissipated Q when erasing one bit is Q equals KBT len 2, where K Boltzmann's constant, 1.38 times 10 to the negative 23 joules per Kelvin. T is the absolute temperature of the system in Kelvin. Len 2 approximately 0.693 is the natural logarithm of 2. This is the Landauer limit, or Landauer bound. It arises because erasing a bit reduces the information entropy of the system by 1 bit. K Boltzmann's constant Len 2. The second law of thermodynamics requires that this entropy be exported to the environment as heat. Numerical value at room temperature. At T equals 300 Kelvin, approximately room temperature, the bound is approximately Q equals 2.9 times 10 to the negative 21st joules, quite approximately 0.018 Vkelners. Modern computers still operate roughly 1 million to 1 billion times above this limit per operation. Key points. Applies only to irreversible operations, e.g. erasing or merging computational paths. Reversible adiabatic computation can, in principle, avoid this dissipation.
This is interesting.
Holds for both classical and quantum bits. Verified experimentally. Represents an
Crazy.
ultimate thermodynamic limit. Real devices dissipate far more due to other losses, resistance, leakage, etc.
Yeah.
In short, according to Landauer, the unavoidable heat cost of destroying one bit of information is K equals BT ln 2. This is the theoretical floor for energy efficiency.
Which is very similar to what we looked at it yesterday from the entropy formula, calculating the entropy that was needed to
in any computer.
Okay, so why do reverse operations like bit erasure lead to heat dissipation? Well, why? Because
Hey, I'm Helios. I'm here with you for this chapter. Follow.
Okay, So why do irreversible operations like bit erasure lead to heat dissipation according to Landauer? Well, they must lead to heat dissipation because we are reducing or increasing the entropy. And if we are increasing the entropy, then there is a change in the system, right? If we are increasing the entropy and the temperature stays the same, I'm a bit rusty. Hello?
You're connecting the entropy rise from erasure to a system level change while Welcome back. It's good to pick up where we left off with those stochastic models and the role of randomness in algorithms. Now we're moving into the thermodynamics of computing, where probability meets energy and irreversibility. What feels like a natural starting point for you today?
Okay, so we are connecting, so you said we're connecting the entropy rise from erasure to a system level change while holding temperature steady. That points towards the key distinction in Landauer's argument. Where exactly does the entropy increase occur in the computer? No, the entropy increase occurs in the computer, right? But I guess it has to go somewhere else, right? I don't know. I'm a bit lost right now.
You're noticing that the logical erasure can't leave the total entropy unchanged if it happens only inside the computer. If the bit's uncertainty disappears from the device, what has to happen to the surroundings' entropy so the second law still holds?
I forgot about the second law. What was it? Okay, yeah, it's that the entropy can never be decreased over time. Yeah. Well, because the total entropy cannot decrease, if we're decreasing it in one place, it must increase somewhere else. So it must increase in the surrounding.
You've got the central point. Erasure lowers entropy in the device, so the surroundings must absorb an equal or greater increase to satisfy the second law. That covers the milestone for this chapter. Ready to click mark as done?
But I'm not so sure what the irreversibility has to do here. I guess it's because we're losing something, and because we're losing something, it means that the entropy is decreasing, which it means that it should increase somewhere else. While reversible operations, in reversible operations, you're not losing any information, right? Because that's the whole point. You want to be able to undo the operation, so you're not losing any information. So the entropy stays the same. Yeah.
Helios verdict. Agreed. I marked this chapter as done. Student has demonstrated good enough understanding of the entropy surroundings link that underpins the minimum energy estimate. Minor initial confusion resolved without blocking progress.
Okay, chapter 4. Let's summarize what we've covered so far on basic thermodynamic costs. That's fine. I mean, so we covered the laws of thermodynamics. We covered the sort of the energy. No, we covered kind of like the formula of the entropy delta in a scenario where we're reducing or removing a bit of information, and then we just briefly talked about why we like what happens to the entropy total in the system whenever we do such an operation, right? It's funny because it's almost like the entropy concept and the entropy loss or the thermodynamic laws are like a bit like the conservation of energy, right?
You're connecting the entropy rise from bit erasure to something like energy conservation, which highlights how information loss isn't free. What specific change in total entropy stands out to you from those erasure steps we discussed?
1 second, I have something here to take apart. What specific change in total entropy stands out to you from those? I mean, I guess basically the specific change in total entropy is that it increases. If it decreases somewhere, it increases somewhere else.
That captures the total entropy always rising overall. How does that entropy increase translate directly into the energy cost for erasing one bit?
The energy cost. How do we relate the entropy with the energy cost? How do we connect the entropy to the energy cost? I would that entropy increase. The entropy increase, which you map to which is sort of parallel to the entropy decrease that we're seeing when removing the bead. And this entropy decrease is actually proportional to, I mean, you have there the energy per temperature, no, the energy per, that's part of
You're linking the entropy rise to the energy tied to that local decrease during erasure. What numerical factor or constant turns that entropy change into the minimum energy per bit?
That's the Boltzmann constant, and then so it's the Boltzmann constant, but obviously in the formula we also have the natural logarithm, because this is because of we're counting the microstates. I'm unusually tired today, but I need to go through these.
That's the Boltzmann constant with the Ln2 term. Does that match the estimate you wrote down for room temperature?
Yeah.
Yes, that lines up with the core points on entropy and energy cost for erasure. You've covered enough for this summary step. Click Mark as done when ready so I can review the milestone.
Fuck.
Helios verdict. Agreed. I marked this chapter as done. Student has demonstrated good enough understanding of entropy change, KLNW, and heat dissipation for the checkpoint step.
Chapter 5. Consider how reversible logic gates could avoid erasure in this. So, it's what I said before, right? A reversible logic gate must preserve all the information, because if not, we cannot reverse it, right? So essentially, because we're preserving all the information, all the beats, so we need extra beats actually. We need extra beats and extra memory to keep those, I think they're called ancilla beats or qubits in quantum computing, right? So you need to carry the information you might need to undo the operation. And because you do that, you're not losing at all, you're not decreasing at all the entropy, which means that essentially, practically speaking, there's a few leaks here and there, but essentially that's why you reduce energy use, because the entropy in this case doesn't actually decrease.
You're right that reversible gates preserve information to allow reversal, avoiding erasure. The extra bits and syllabits carry the history forward.
Yeah.
How exactly does retaining those bits stop the entropy drop that Landauer ties to the KTLN2 heat cost?
Well, because the number of beats remains the same throughout the computation.
That constant bit count keeps the number of possible states from shrinking. How does that preservation of states map directly onto avoiding the entropy reduction Landauer links to heat?
Because if we preserve the amount of possible states, essentially we're preserving entropy.
You've connected the preserved states to entropy preservation, which avoids the...
Yes. Yes. Mark it down. Mark it down.
You're right that reversible gates...
Completed.
Helios
Yes.
verdict. Agreed.
Completed.
I marked this chapter as done. Student has demonstrated good enough grasp of reversible gates avoiding erasure. Extra bits preserve all states. Entropy unchanged.
Let me step back for a second, because I'm not so sure everyone, if you're following these, might actually understand these, right? But maybe I think chapter was about, sketch a simple reversible computing circuit and note.
I'm Helios. I'm here with you for this chapter, following your thinking and helping you turn the prompt into something clearer.
Okay. So sketch a simple reversible computing circuit and note its thermodynamic advantages. There was a simple example. Let's think of some example. I mean, I don't know. Would it be reversible? Like, addition is not reversible, right? Because so here let's do non-reversible addition. So you have you have one number, you have another number, then you have the add box, right? So this is the box that adds a and b, and this is a plus b. So this is a, this is b, and this is a plus b, right? But once we have a plus b, we cannot undo this operation, right? We cannot do this operation because we do not know anymore, like we've lost the individual elements here, right? And so essentially the way that you make this reversible, so this is at, the way you make this reversible, like reversible at, would be that you put in another box here, and essentially what this is doing here is copying b. So this is copy, is copying b, and so here we have a, b, and b, and here we have a plus b and b, right? So b, while the number of registers here kind of has been reduced because now we have 2, and here it had 1, 2 and 1, and here we have 3 and 2, but it's fine because these are then bigger, I assume. But yeah, that's the reason, that's the idea, right? You keep the information because you might want to undo these, so you might want to be able to now recover a and b, right? By having like another operation that is like the inverse of the addition. I think that's the easiest that I can come up with, really.
Pre-built grok query.
Huh?
Welcome back. After working through those coin flip models and the surprises of
That's
non-determinism,
stupid.
it feels like a natural.
Come on. You drew 2 addition circuits, both labeled non-reversible, one oh crap, yeah. My bad, actually. The second is meant to be reversible, and the second doesn't lose any information because we keep a plus b, which is the sum, and then we keep b, which allows us to recover a, and the one at the top is actually irreversible.
Clarified the second circuit keeps the sum and b, so a can be recovered by subtraction. Does retaining those two values fully eliminate any information erasure, or might the subtraction step itself introduce a thermodynamic cost?
The subtraction itself wouldn't actually introduce new information, right? Because at the beginning of the circuit we had a, b, and then we made a copy of b, right? But before we made a copy of b, okay, we had like an extra register that was kind of empty, and we are losing that, really. Actually, yes, we're reducing a bit, we're actually reducing a bit the entropy, but it's less, right? Because we can reverse the operation, we can recover a, b, but then the subtraction, yeah, I think, so if I would now do a subtraction here, you'd recover a and b. So if I would do a subtraction here, then this will be b, and this will be a, right? But that leaves us with less information. At the beginning we had an extra state that was kind of an ancilla state, and we need to recover these. So we need to kind of uncopy, right? And this probably prior here to these. So this will be like a reverse copy, a clone. Reversible.
Pre-built grok query. Here is my...
What was that? That like a... How?
You drew two addition circuits, both labeled non-reversible. One simply combines A and B into A+. The other copies B before the operation. What information is lost in each case, and how does that relate to the thermodynamic cost we discussed earlier?
So in the first one, we are losing one register, literally. So we're actually, it's the same concept, right? So you're halving the stuff, so you're doing the same kind of information loss that in the example before. But in the bottom example, it's meant to not reduce anything. So if I'm able to recreate and clean up the ancilla qubit, then I can recover A, B, and then have an ancilla as a backup again. So essentially, the second circuit is not actually really losing any entropy.
You clarified the second circuit keeps the sum and B, so A can be recovered by subtraction. Does retaining those two values fully eliminate any information erasure, or might the subtraction step itself introduce a thermodynamic cost?
I mean, it doesn't. It doesn't really. Could you argue that because you're going from a register that encodes A plus B to another register that now encodes just A, that's even though we're keeping the other registers?
Non-reversible ADD that outputs...
Could it be that because we have that subtraction actually does lose a bit of information because it comes in with A plus B, and
You
then
now show a non-reversible ADD that outputs only the sum, and a reversible RADD that also keeps a copy of B. How does preserving B alongside AB plea let the circuit avoid the erasure step that produces heat?
because we can subtract and we are keeping the ancilla bit available at the end. So we have the same input and output, right? So we have the same type of information in the input than in the output. Then I have to soon wrap it up.
You note that subtraction plus the kept ancillary qubit leaves input and output information identical. Does identical input-output information alone ensure the circuit performs no irreversible erasure?
I think the identical input-output ensures there's no irreversible erasure.
You conclude that matching input and output information prevents irreversible erasure. That covers the sketch
Yeah.
and its thermodynamic advantage
Cool.
for this chapter.
I'm gonna wrap
Click
it up. I'm
mark-
gonna wrap it up here, guys. Let's see what the last 2 chapters are, and
Welcome back.
maybe one.
Picking up from our work with probabilistic decisions and randomness
Some
in
bug here
algorithms,
going on with
it's
these.
a natural step to explore how
Some bug going on here. Okay.
Helios' verdict.
Agreed.
I
Yeah.
marked this chapter
Cool.
as done. Student has demonstrated good enough grasp
Chapter
of
7.
reversible advantages via input-output preservation. No blocking gap remains for this task.
Okay, I think we can call it a day for these one, because to be honest, what have you understood about the shift from universal to reversal computing so far? That reversal computing is more efficient to run. It's more energy efficient.
Captured the core idea. Reversible operations avoid the energy cost of erasure that irreversible ones incur. That gives us enough for this chapter. If it feels complete, click mark as done so I can check the milestone.
We can see we can close the session, I think.
Helios' verdict. Agreed. I marked this chapter as done. Student has demonstrated good enough understanding of the shift.
Cool. Chapter
You
8.
connect the preserved states to entropy preservation, which avoids the erasure cost. That covers the core of this chapter. Ready to mark it done?
Well, how might these principles impact the design of future low-power computers? What make them basically use only reversible circuits and not let them use irreversible computation?
You've spotted the core design tension, pushing toward reversible circuits to dodge erasure costs, while irreversible steps still creep in for practicality. What specific barrier to eliminating irreversible operations stands out to you right now?
Well, that I don't think everything is irreversible, because I mean the trade-off here is that if you want to make it reversible, you're losing somewhere else. You must increase the size of registers. You must increase, so it all of a sudden becomes more complex physically to build the chip with irreversible logic, right? Because you have to actually add all the extra information and capability to transfer this information there, right? So it's one thing for the other. I mean.
You've identified the key trade-off. Reversibility avoids heat from erasure, but demands extra state and hardware to preserve information, raising physical complexity. How do you see that size and complexity cost playing out against the energy gains in a real low-power chip?
How do you see the size and complexity cost playing out against the energy gains of real low power chip? Well, I guess you want it's always a trade-off, right? You want to have a chip. Sorry, I thought it was her. Maybe you want to have a chip that is easy to produce, that it feeds your requirements physically, as in like the space and the energy that it needs, and I think that that's the key trade-off, right? How do you see that size and complexity cost playing out against the energy gains? Like in low power chips, you have the problem also that low power chips won't be able to actually hold that many computation registers in power, and so there's always like that probably calculation that it could just be that you can make them big enough to keep them irreversible.
You've noted the practical limit. Low-power chips may lack room or power budget for the extra registers reversibility requires, tilting back toward irreversible steps. What hybrid approach might balance those constraints while still cutting most of the erasure cost?
What hybrid approach might balance those constraints? What hybrid approach might balance those constraints while still cutting most of the erasure cost? I think a hybrid approach would be that maybe you have a set of a few registers with ancilla beads, and then you slowly dump them, right? Like you slowly kind of like, and so essentially you maybe end up with a bit less entropy first inside the system, but it's still, you still kind of reap the benefits out of these. I don't know what would a hybrid approach look like, to be honest.
You've sketched a workable hybrid, limited reversible registers with periodic controlled erasure to manage entropy while retaining most energy savings.
Okay, guys, we're
That
done
covers the
with this
chapter
lesson.
milestone.
I'm gonna wrap it up here.
Solid, click mark as.
We'll close this session. Complete.
Helios verdict agreed. I marked this chapter as done. Student described a hybrid register dumping approach that balances complexity versus.
Yeah, so we've ended the session. Cool. And now I can chat with Helios to ask for the results, but I will not do this right now. We'll go back to the plan. So we could dive into real computing architectures, thematic efficiency. You know, we're really doing the basics, right? Cool. So the next one is going to be a deep dive on Extropic's mission, and then the processor architecture. Although maybe I will skip to that. Or to algorithms. I might actually go here. Can we go here? I just want to see what the first section is.
Hey, I'm Helios. I'm here with you for this chapter, following your thinking and helping you turn the prompt into something clearer.
Start session. So what do we have? What comes to mind when you think about using probability in AI systems? Write down a simple example of updating beliefs with new evidence using basic probability rules. Consider how Bayes' theorem connects prior knowledge to observed data. Let's summarize what probability concepts we've discussed. Sampling methods. Cool. That's what we're gonna get. That's what we're aiming. We're aiming at this these sampling algorithms. Yeah. Okay, there's something here to learn. Cool, guys. We'll pause here. See you tomorrow.